Hello everyone, myself Nigaraj. I am explaining OS assignment. My assignment is on the Robin round time scheduling using a different time quantums. First of all, we go on introduction. Introduction. In this assignment, I am implemented and compared the round robin CPU scheduling algorithm. Scheduling decides which process gets CPU time. Round robin is a primitive algorithm where every process get a fixed time quantum and a process will execute in a cyclic order. The objective was to test four time quantums 2, 4, 6, and 8 ms and find which one gives the best performance. Moving on experimental setups, I used a C programming language and I compiled it in using a GCC. My dataset contained five processes with a burst time 10, 5, 8, 6, and a 12 milliseconds. These processes were tested with a four time quantum values to compare their waiting time, turnaround time, and a context switches. So we moving on implementation setups. I created a process structure, stored burst time, and then simulated the round robin cycle. Each process was executed for a minute, remaining time, and quantum, and if not completed, it was sent back to the queue. Finally, I calculated the average waiting time, turnaround time, and the context switches for each quantum. Moving on to the flowchart. A flowchart shows that how a round robin works. All processes enter a ready queue. The first process is taken and given CPU for one time quantum. If it is still has the remaining burst time, it goes back to the end of the queue. If it is finishes, it turnaround time is recorded. This cycles continues until all process finishes. This usual explains the circular behavior of a round robin. Now moving on to the code explanation. Structure definition. A process structure stores a PID, burst time, remaining time, waiting time, and a turnaround time. Run RRR function. This function performs a round robin scheduling. It starts by making a deep copy so each quantum test is fresh. A loop runs until all process finish. Now moving on to the execution loop. For each process, execute it for minute, time quantum, and remaining time. Reduces remaining time, increases global time. Increases waiting time for all other active processes. If a finishes, the turnaround time is recorded. If not, it is placed back into a queue. RRR behavior. Calculating averages. After all processes finishes, the program calculates the average waiting time, average turnaround time, number of context switches. Main function contains a data set of five processes. Call run RRR four times with a quantum values 2, 4, 6, 8. And now moving on to the output. The output shows for each quantum the time progress prints waiting time, turnaround time, and context switches. Example pattern observed quantum 2. Now here the quantum time is 2 milliseconds. Highest waiting time and a maximum context switches. In another case, quantum time is 4 milliseconds. Improved performance. In another case, quantum time is 6 milliseconds. Best results with a balanced waiting time and a fewer switches. And last one is quantum time is 8 milliseconds. Fewer switches but slightly higher waiting time for shorter processes. Moving on the observation. This is our Gantt chart. Observation. My main observations were small quantum is equals to more context switches. Larger quantum is equals to behavior more like a FCFS. That stands for first come first serve. Medium quantum gives a best balance. Waiting and turnaround times steadily decreases until quantum is equals to 6. Next, comparative evaluation. After comparing all the four quantum, I concluded that a 6 millisecond is the optimal quantum for this dataset because it balances a fairness and a efficiency better than the others. Next, short analysis. From the comparison, 6 milliseconds gave the lowest average waiting time and turnaround time with a reasonable context switches. Quantum 2 wasted the CPU time due to too many switches. Quantum 8 increased the waiting time for a smaller processes. Therefore, for this dataset, 6 millisecond is the most efficient quantum value. So here I conclude that round robin is a performance depend heavily on choosing the right time quantum Through this experiment, 6 milliseconds proved to be the optimal choice for the balancing fairness, responsive, and efficiency. Thank you.